So now let's kind of change gears a little bit and talk about what happens if a hydrogen atom has more than one electron. Perhaps you've heard that the ground state of hydrogen, that shell can hold 2 electrons, and you may have wondered, why is that? Well, it turns out that it boils down to something called the Pauli exclusion principle, and what that principle says is if an atom has more than 1 electrons, no two can have the same set of quantum numbers. So what we kind of mean by that is we know that n is going to dictate L, and L is going to dictate m sub L. Now we also have another quantum number, m sub s, which is going to be equal to, plus or minus 1/2, and that's not really dictated by L. So considering the n is equal to 1 state, that forces L to be equal to 0, which forces m sub L to be equal to 0. So this is the 1s state of hydrogen. Now we can only have 2 electrons that live inside of this state, and these 2 guys right over there are going to correspond to m sub s is equal to plus or minus 1/2. So the spin is what allows more than 1 electron into that particular state. Considering that n is equal to 2 state, that's going to allow L to be equal to 0 and L to be equal to 1. That dictates m sub L is going to be equal to 0. This one here dictates m sub L could be equal to -1, 0, and 1. And much like before, the 2s state can only hold 2 electrons, and that's going to be the up spin and the down spin electrons. Now, we only have one L state, so we have 3 states to play around with. Each of those states can hold a spin up and spin down electron, so we're actually going to have 6 possible states that exist in this one, and inside of this n equal to 2 or L shell, we can actually hold 8 electrons. You can kind of convince yourself as we work our way down the table, increasing in n and increasing in L, we can hold more and more and more states, and therefore more and more and more electrons. Keep in mind that it is the spin that dictates the 2 electrons per state. So let's go ahead and apply the Pauli exclusion principle to the 3-dimensional box. Again, we cannot have 2 electrons in the same state with the same quantum numbers. And let's take a look at the ground state. The ground state is going to have just 3 quantum numbers, and x is equal to 1, and y is equal to 1, and z is equal to 1. So this guy right over here can only hold 2 electrons, just like the hydrogen atom can. It can be the spin up and the spin down. Now the second energy level, 2e1, that one is actually 3 times degenerate, and so we can have nx equal to 2, 1, 1, or 1, 2, 1, or 1, 1, 2, and each one of these can hold an up-down electron. So there's the first one right over there. This guy right over here can hold an up-down electron. There's a down electron. And this guy right over here can hold an up-down electron. So that state can hold 6 electrons. And we can kind of work our way up the box and convince yourself, how many electrons can each state hold. Keep in mind that, if possible, the electrons will try to fill up the lowest energy level states first. So let's, for a second, consider another multi-electron atom. Let's consider lithium. Lithium is going to have 3 protons and 3 electrons. And where are the electrons going to go? Well, what the Pauli exclusion principle says is inside of the 1s subshell that we can only have 2 electrons. We can have the spin up and the spin down electrons, and so the third electron has to go into the 2s subshell. And what this guy is going to look like is this guy right over here, the innermost shell, is going to get 2 of those electrons, and then this subshell is going to get that electron right up there. So that kind of leads me to the relative sizes of the atoms as we look inside the periodic table. Now here we have the hydrogen atom, and here we have the helium atom, and the helium is just a little teeny tiny bit smaller because those 2 electrons that live inside of the 1s subshell are kind of pushing on each other and being pulled into the nucleus. And then when we pop up to lithium, we have that third electron that we have to worry about, and that's going to pop us up to the next subshell. And actually, as we add more and more and more electrons, it's going to shrink some of the innermost shells, which is going to shrink the size of the outermost shells. And then we're going to be at a maximum right over here. And this is also a noble gas, which tends not to give up its electrons because the shell is full. And then we're going to pop down to sodium, and that's going to go up to the next subshell, so the atom is going to jump up drastically in size. Remember, the size of an atom is dictated by the outermost shell. And then the same thing, we're going to add electrons and shrink down till we hit argon, the noble gas. Again, doesn't like to share its electrons, and then pop, we're going to go up here to the next subshell, and so on and so forth. So what this guy kind of looks like in a table is hydrogen is going to have 1 electron inside of the 1s subshell. Helium is going to have 2 electrons, both inside of the 1s subshell, and this is the spin up and spin down electrons. And then we pop up to lithium, which gets the 2s subshell. We go to beryllium, which is going to have an additional electron. It's going to fill up that subshell. And we're going to pop up to boron, which we know that the 2p can actually hold 6 electrons. And so they're there, 1, 2, 3, 4, 5, 6. And then we have to pop up to the next subshell, and so on and so forth, working our way down the periodic table. Now, how about the energy levels of other atoms? Well, it turns out that's really actually quite complicated. What we can do is we can kind of generalize in a very, very, very rough approximation that the energy levels are going to kind of go like the hydrogen atom, 13.6 electron volts, divided by the quantum number n squared, multiplied by z squared, where that is going to be essentially the number of protons. And that's going to be kind of close. Actually, it's going to be a lot more qualitative than quantitative, so not particularly useful in terms of calculating energy levels, but it's a good enough approximation for, well, at least physics 243. One thing to kind of keep in mind when we talk about multi-proton, multi-electron atoms is that first of all, there's going to be some interaction between all of those electrons that are going to mess with those energy levels. And secondly, if you recall Gauss's law, some of the electrons in the outer shells are not going to see some of the inner shells because they're kind of screened by the electrons in the inner shells. And so actually it's not really going to be so much as a z multiplied by the number of electrons, but kind of like a z effective, where z effective is going to be less than z. So while we're talking about multi-electron atoms, let's talk a little bit about something more useful for something like forensics. Let's talk about X-ray spectroscopy. So if you were to take any atom and you were to bombard it with high energy electrons, then what can happen is you can emit X-rays, and kind of keep in mind that there is always going to be some minimum wavelength with which you can emit, and that's related to the accelerating voltage of the X-ray tube. And if we were to kind of look at the intensity of some X-rays coming off of some atom, you're going to see some minimum guy right over there. And then we're going to kind of see some continuous spectrum, and then we're going to see some sharp peaks. And they're actually called the K beta and K alpha lines, where the K alpha is the most intense short wavelength that comes off, and the K beta is kind of the first one. And what's kind of happening here is these high energy electrons are being absorbed by some of the innermost electrons of the atom. And that's not going to be what we see when we shine light on something. Usually we're messing around with the outermost electrons because they're more loosely bound. However, X-rays have a whole lot of energy. So what we're doing is we're knocking one of those inner electrons up into a much higher energy state, kind of creating a hole down one of the inner shells. We're going to see these sharp peaks where one of the other shelled electrons are kind of dropping in to fill out that hole. Probably not surprisingly, because all the atoms are going to have characteristic shells at different energy levels. Then different elements are all going to emit different X-ray patterns at different frequencies. And so this is kind of like a fingerprint of atoms, if you will. So it could be very useful for something like forensics, where if you fire a gun, then you could kind of take a look at the dust that's on someone and see if it has the same spectra that you would see from gunpowder. So a fellow by the name of Moseley was taking a look at the K alpha, that's again the most intense short wavelength line that we saw, and he noticed that the emission was proportional to the atomic number z minus 1, and it was kind of directly proportional. What he found was the larger z means a higher frequency and more energetic X-ray photons were emitted, and he came up with this law right over there that kind of describes the frequency with the atomic number, and this is just kind of an empirical fit right over here. And this is kind of consistent with what we would expect when what we're kind of doing is we're using high energy electrons to knock energies out of the K shell, and then when an L shell electron falls in to fill that hole, then we're going to have an X-ray that is produced. And since the energy depends on Z, then so also does the energy of the electron that is released.